monotonicity matters. Do you remember the statement of the alternating series test? So here's what the alternating series test tells us. If I've got a sequence, the terms of which are decreasing and they're all positive, and the limit of a sub n as n approaches infinity is 0, then the alternating series that I build using the sequence a sub n, the sum n goes from 1 to infinity of -1 to the n plus 1 times a sub n. So this is an alternating series. This alternating series converges. I've been assuming that the sequence a sub n was decreasing, and I used that to get that the even and the odd partial sums were monotone. But what happens if I get rid of that condition? What happens if I get rid of the condition that a sub n is decreasing? Well, let's break the alternating series test by removing this condition. I'm going to remove the condition that the sequence a sub n be decreasing. I could call this the broken alternating series test. I'm just going to assume that the a sub n's are positive and that their limit is 0. And if I just make these two assumptions, is it then the case that this alternating series necessarily converges? So to see how broken this really is, the question is this. Can you think of an alternating series where the terms are going to 0, but the series diverges? Well, here's an example. It's a sequence a sub n, and the definition depends on whether n is odd or even. So if n is odd, it's 1 over n plus 1 divided by 2. And if n is even, it's 1 over n over 2 squared. Well, what does this look like? I'm going to use this sequence to build an alternating series. And what is this alternating series then looking like? Well, I plug in n equals 1, and that's odd, so it's 1 over 1 plus 1 over 2, it's 1 over 1. I plug in n equals 2, I get 1 over 2 squared, but that's going to come with a minus sign. I plug in n equals 3, it'll be 3 is odd, so it's 1 over 3 plus 1 over 2, it's a half. I mean, here's some of the terms. I've just started writing them down. Right, so it's 1 over 1, and then minus 1 over 1 squared, plus 1 over 2 minus 1 over 2 squared, plus 1 over 3 minus 1 over 3 squared, plus 1 over... I mean, what this really amounts to is sort of weaving together two different series. Right? The positive terms are the harmonic series, and the negative terms in this alternating series are the p series with p equals 2. And the limit of the nth term is 0. Well, specifically, the limit of the odd terms here is just the limit of 1 over n, and that is 0. And the limit of the even terms here is just the limit of 1 over n squared, and that's also 0. So putting together these two facts, just the limit of a sub n is equal to 0. But the sequence, it's not decreasing. If I look at the terms, right, just the first few terms of this sequence a sub n, I mean, these are not decreasing. Right? I mean, look, 1/2 and then 1/4, but then 1/3, right? It's going up here, down here, up here, down here, up here. It's not a decreasing sequence. And the alternating series diverges. So I want to look at the sequence of partial sums s sub 2n. The sum k goes from 1 to 2n minus 1 to the k plus 1 times a sub k. Now the whole thing about this series is that it's weaving together the harmonic series and a p series with p equals 2. So this partial sum can be written like this. The odd terms are the harmonic series, and the even terms are giving me this p series with p equals 2. The odd terms are positive and the even terms are negative. So this partial sum is this. It's the sum k goes from 1 to n of 1 over k minus the sum k goes from 1 to n of 1 over k squared. Now the whole point here is that the harmonic series diverges, and this is a convergent p series. So that means by taking n large enough, I can make this harmonic series, or this partial sum for the harmonic series, as large as I'd like. But no matter how big I take n, this convergent p series never exceeds the true value of this p series, which is pi squared over 6. So what happens then when n is really large, right? This term becomes very, very large as I'd like. This term never exceeds the value of the convergent p series with p equals 2. And that means that the limit of these even partial sums is infinite. And consequently, this series diverges because the limit of the partial sums doesn't converge. Well, this is a particular philosophy by which you can study the whole world. If you want to know that car engines are important, well, you take the car engine out and the car doesn't go. So it must have been important. Well, the same sort of game is being played here with the alternating series test. I took out a part of the alternating series test. I've removed the assumption that A sub n is decreasing. And then I saw that the alternating series test didn't work anymore. So although I don't emphasize it all the time, the fact that the A sub n sequence is a decreasing sequence really is important when you're applying the alternating series test.